Hello everyone. In this video, I am gonna talk about solid design principles. These are 5 principles introduced by Robert C. Martin, and they really guide us as to how you should build your applications, specifically how you should build your classes. So solid is an acronym, and you will see the meaning of each of the letters as we go through this slide. Let's start with the first principle, that is single responsibility. This means that a class should be responsible for one thing and has a one reason to change. For example, if you are designing a class to manage user authentication, then that class should only handle tasks like validating credentials, nothing else. Then there is an open close principle where classes as you build them should be available for extension if another class wanted to use the parent class. However, it should not be open for modification, meaning that you should not have to change the internals of the class in order to use it. By the way, a lot of these principles have to do with inheritance. For example, the Liskov substitution principle says that any derived class should be substitutable for the parent class. So anywhere you can use the parent class, you should be able to use the child class or the derived class. A very similar principle is the interface segregation principle. This says that a class should never be forced to implement unusable interface. So essentially, the interface should be specific to the classes that are deriving from it. And then finally we have the dependency inversion principle, which says that high-level modules must not really dependent on low-level modules, and you will see as we go through the examples in the next section. Now let's start with an example that violates the single responsibility principle. In this example, the report class has multiple responsibility like generating the report, printing the report and saving the report to a file, which violates the single responsibility principle because any changes in the way the report is printed or saved will require a change to the report class. To follow the single responsibility principle, we can refactor the code by separating the responsibilities into different classes. Let's take a look at this example which following the single responsibility principle, where report class represent the report's data like title and content, and report generator handles the generation of the report, and the report printer handles the printing of the report, and report saver class handles saving the report to a file. By separating these responsibility into a different classes, each class now has only one reason to change. For example, if the printing logic changes, only the report printer class needs to be modified without affecting the other classes. Now let's see the example of open close principle. In this example, the area calculator class violates the open close principle because if we need to add a new shape such as a triangle, we would have to modify the calculate area method, which requires changing the existing code. To follow the open close principle, we can use polymorphism. So instead of having a single class which handle multiple types of shapes, we can create an abstract base class or interface which extend it for each shape type. So in this example, there is an abstract base shape class with an abstract method calculate area, and concrete classes like circle, rectangle and triangle that extend shape and implement the calculate area method, and a class area calculator that calculates the area by calling the calculate area method on a shape object. By using this approach, the area calculator class is now open for extension but closed for modification. If you need to add a new shape such as a triangle, you can simply create a new class that extends shape and implements calculate area without changing any existing code in the area calculator class. So this follows the open close principle and makes system more maintainable and scalable. Now let's move to the Liskov segregation principle and consider an example involving a bird class and penguin subclass that violates the Liskov segregation principle. In this example, penguin inherits from bird, but it cannot fly. The fly method in penguin will throw an exception. This violates the Liskov because if you substitute a bird object with a penguin, it breaks the expected behavior, leading to a runtime exception. To follow the Liskov, we need to redesign our classes. To avoid this problem, one way is to do this to create a more appropriate inheritance structure or use interfaces. Let's look this example where a base class bird with general bird behavior like eat and an interface iFlyable for birds that can fly, and a sparrow subclass of bird that implements the iFlyable because it can fly, and a penguin subclass of bird that does not implement iFlyable because it cannot fly. By refactoring this design, you avoid the need for a fly method in penguin that throws an exception. So this follows the Liskov substitution principle because substituting a bird object with any of its subclass will not cause unexpected behavior. Now let's look with an example that violates the interface segregation principle. In this example, the iWorker interface is not following the interface segregation principle because it forces robot worker class to implement methods like eat and sleep, which are irrelevant to robots. The robot doesn't need to eat or sleep, so these methods are not applicable and will throw not implemented exception. To follow the interface segregation principle, we should split the iWorker interface into smaller, more specific interfaces. So interface iWorkable for work related operation and interface iEatable for eat related operation and interface iSleepable for sleep related operation. So human worker implements all three interfaces because a human can work, eat and sleep, and robot worker implements only the iWorkable because a robot only needs to work and doesn't need to eat or sleep. By following ISP, we ensure that classes like robot worker are not forced to implement methods they don't need. This leads to a more modular and maintainable code base. Now let's move to the last solid design principle, that is dependency inversion principle. And if we take a look on this inversion principle, the report generator class depends directly on file logger class. This violates the dependency inversion principle because report generator is tightly coupled to the file logger. If you want to change the logging mechanism, you would need to modify the report generator class. To follow the dependency inversion principle, we should depend on abstraction instead of concrete classes. Here's how you can refactor the code. You can see iLogger interface represent the abstraction for logging. File logger and the database logger are the concrete implementation of iLogger that provide specific logging mechanism. And report generator, a high level class that depends on the abstraction iLogger rather than on concrete logging implementation. The specific logging implementation is provided via dependency injection. So this design follows the dependency principle by ensuring that high-level modules depend on abstraction rather than concrete implementation. So these are the examples of the solid design principle, and I hope you got some basic understanding of this solid design principle. Thanks for watching this video.